good afternoon to all my dear lovely students. I hope all of you are doing great and studying well for your RE-NEET exam, which is on 21st June. I welcome you back to the YouTube channel Shri Chaitanya Educational Institution, and where today we are going to talk about two of the most important chapter from the organic chemistry point of view, because almost 80 to 90% of the reactions which are there in your syllabus get covered in these two chapters, which are going to be alkyl and aryl halides, followed by alcohol phenols. Okay, so we'll be talking about these few topics. I have taken the most important previous year questions of NEET and some JEE questions as well, in order to make you revise this chapter in a more smarter way. Okay, so let us start with our first concept. Okay, if we read the question carefully, benzene diazonium salt is prepared by reaction of aniline with nitrous acid at 0 to 5 degrees Celsius. It decomposes readily in the dry state. Okay, which is absolutely correct. We know that diazonium salts are unstable above 5 degrees Celsius, so around 10 degree and all, it will decompose easily into phenol. Insertion of iodine into the benzene ring is difficult, and hence iodobenzene is prepared through the reaction of benzene diazonium salt with Ki. This is also absolutely correct. Both the statements are absolutely correct here. As we know, iodination of benzene is a reversible process and it's a very slow reaction. You don't see much of this reaction. Iodine in the presence of AlCl3 we cannot do. Instead, we take iodine in the presence of HNO3. Okay, which is still a slow reaction. This HNO3 oxidizes the byproduct Hi back to I2 and somehow makes this reaction to happen. But this is not the way to prepare your iodobenzene. The better way to prepare iodobenzene would be to start from a diazonium salt and react it with Ki. So yes, these are two correct statements. It's a last year NEET question only. Okay, so moving ahead to the next one, which says, which of the following reaction does not give benzene as the product? Which of the following reaction does not give benzene as the product? So if we look at the reaction, alkynes aromatization. So this is not aromatization, this is cyclic trimerization of alkyne in the presence of red hot iron 600 degrees Celsius. This will give benzene, as we know. This is going to give us benzene. Next one is a diazonium salt with water. This one will give you phenol. This is the preparation of phenol. If you want a benzene from diazonium, you need to do reduction of diazonium salt using either H3PO2, which is phosphenic acid. Okay, phosphonic acid, sorry. Phosphonic acid you can use, or you can use ethanol for the reduction. This is decarboxylation by soda lime. This will obviously give you benzene, benzoic acid decarboxylate to give benzene. And this is aromatization. Last class we have seen this reaction as well. So yes, B doesn't give you benzene, but it gives you phenol. Okay, few questions I have taken from benzene chapter as well, aromatic compounds as well. Let's look at the next question, a very nice question, which is coming from the preparation of alcohols and also reaction from the preparation of ketones as well. Okay, so two reactions are happening here. If you see carefully, this is a Grignard reagent, which is a carbon with a negative charge, magnesium with a positive charge. Very important question. Many of the students made blunder mistakes here. Whenever you take a Grignard will first of all attack on any acidic proton. I don't find anyone here. So otherwise it will do nucleophilic addition reaction. This carbon is also partial positive, C triple bond N I'm drawing like this. This is also partial positive. So Grignard can attack here, converting it into a salt, O minus MgBr plus, which is going to look like this. So a methyl has attacked here. This become O minus MgBr plus. On the other hand, when it attacks on a nitrile, functional group, it converts it into imine functional group, imine. So we get a salt of imine here. This carbon got attacked by a CH3 and we get double bond N minus MgBr plus. Right. So in the first step, reaction would have stopped here completely. In the first step, nothing else will happen. This imine will not get attacked by another methyl group. Okay. Now they are doing hydrolysis step 2. When you do hydrolysis, O becomes OH. And this carbon, the C double bond N, this will hydrolyze to give you ketone. So oxygen comes here and the two hydrogens go here. So we get it as a ketone C double bond O CH3. Okay, C double bond O CH3. Further, do not do another attack of a Grignard reagent here because in the first step it was excess. After hydrolysis, again we have not taken any Grignard reagent. If I do another Grignard reagent as a third step, RMGX, yes, then in that case here also a tertiary alcohol can form. Okay, here also a tertiary alcohol can form, but till the time it's not mentioned, again, so cyanide always converts into ketones on the attack of Grignard reagent, never into alcohols directly. It's a preparation of ketone. Right, so we get our answer. We get a ketone here and we get another methyl here, ketone here, another methyl here, which is D option. Many students had marked option A, which is incorrect. If you want option A, in the third step, we will need another mole of Grignard reagent, followed by another hydrolysis. So a nice question. Next one, moving on to the next one. Assertion reason type question. They say this is iodobutane. Iodobutane undergo SN2 reaction faster than chlorobutane. Answer is absolutely correct. Reason is I minus is a better leaving group than Cl minus. So whether the reaction is SN1, whether the reaction is SN2, E1, E2, any reaction, iodides always are more reactive than chlorides. Iodine is a better leaving group. Yes, that's correct. Because of its larger size, you could say, its poor basic strength, you could say. The one which is a poor base is a good leaving group. So leaving group ability depends on larger size, we can say that is correct only. So this is the final one. So F minus is a very strong base because of its small size. That means it's a very poor leaving group. Whereas I minus is a very weak base and it's the best leaving group out of the halides. So that's the assertion is correct, reason is correct, and it's the correct explanation as well. Right? A very good question from nucleophilic substitution. Next one also from nucleophilic substitution, SN1 mechanism. As soon as we go to SN1 mechanism, we know it happens in two or more steps, where the first step is always going to be formation of carbocation, where the leaving group goes out. Question is, which is undergoing SN1 reaction with the fastest rate, means best carbocation, yet they are asking to draw. Best carbocation. Wherever carbocation is stable, Rx, X minus leaves, in the rate determining step, carbocation gets formed and its stability decides everything. Right? So if I look at it, this is a very poor carbocation, a phenyl carbocation, we know is very, very unstable. It's on a highly electronegative carbon, a doubly bonded carbon, would never want to keep a carbon cation. Next one looks very, very good carbocation, which is a benzylic carbocation, which has 3 hyperconjugations also present from here, and a benzene ring is also helping it in the resonance. It's a benzyl carbocation, which is very, very stable. Next is a secondary carbocation, also good, but nothing as good as the benzyl, so it is also fine only. Not a benzyl, sorry, this is a primary one. Once I remove the Br minus from here, nothing special about this carbocation. As we can see, it's a primary carbocation, which has only one hyperconjugation, not at all good. It's also unstable one. This one is going to be a secondary one, which is also not that great as compared to the benzyl, still better than the C. So one mistake you could do is, if you are like completely mugging it up like primary carbocations are not good, then secondary are better. You may have chosen this answer thinking that it is a secondary carbocation, but no, inductive effect or hyperconjugation effect are not that important. Most important effect is resonance. So resonance decides it. This one will be the best. Okay, although this is also secondary. Even if they did not give this and they gave just a primary one, primary benzyl, that also would be, this one would also be better than the secondary one. Okay, so don't do a mistake of just looking at the degree. You can go wrong. Good question. Next one. Major product A and B formed in the following reaction sequence are. Okay, all of you, I want you to try these reactions. PBr3, so chapter is alcohol. On the alcohol chapter, PBr3 means nucleophilic substitution by SN2 mechanism. Okay, so Br minus replaces the OH minus. Okay, the mechanism is not there in our syllabus, but Br minus finally replaces the OH minus. So we get it as 2 methyl 1 bromo cyclohexane. Then they are doing alcoholic KOH, which is a E2 elimination reaction. Beta deprotonation will happen. There are 2 beta protons available for us here. I can see 1 beta proton here. I can see 1 beta proton here. This is also beta proton. This is also beta proton. The one which gives you a ZZ product we will do. So as we can see, if I remove this beta proton, sigma become pi, Br minus goes out. It gives us a very stable alkene as the major product, which is this one. Other minor product would be from that beta proton, and we get the other product to be this. This will be minor because it has less hyperconjugation. This is going to be major. It is a better alkene overall. Okay, so A is not this, A is this, B is this. So we get it as option C. Okay, we get it as option C. Other are not correct ones. Here, this is the minor one, not even the minor one. This is not even a product. This is anyways a wrong product. This is the correct product, which is the major one, ZZ product. Okay, I hope it is clear to everyone. Moving on to the next question. This is a simple question from the classification of compounds. When we take a alkyl halide, we have different types of alkyl halide. Some of them can be allyl halide, benzyl halide, aryl halide, vinyl halide. So when we take halides, whenever a sp3 carbon is directly attached to halogen, this is a alkyl halide, all of us know. But when this sp3 carbon is directly bonded to a sp2 carbon, like this, then it is called as a allyl halide, allylic halide. But when it is attached to directly to a sp2 carbon of a benzene ring, if this sp3 carbon is attached to a phenyl ring, this we call it as benzylic position. So this is benzyl halide. When benzene is directly attached to halogen, when the phenyl ring is directly attached to your halide, this is called as aryl halide. Similar to aryl, when it is attached to a sp2 carbon directly, which are very unreactive for the reactions, substitution reactions, this is called as vinyl halides. Vinyl, aryl, benzyl, allyl. Accordingly, I can see here, this is sp3. So next to it, there is a, so this is the allylic position. It is a allylic position. So it's a allylic secondary halide. Vinylic, no. Benzylic, no. It's not on the benzylic carbon. Arylic, no. It is not directly attached to the benzene ring. It is a allylic halide. Okay. So this is how we can remember the different types of classification of halides. Consider the following reaction and identify the product P. Chapter is alcohol. Reaction is reaction with HBr, which is a nucleophilic substitution reaction. This reaction and Lucas test are same ones. They undergo by SN1 mechanism. Why SN1 mechanism? Because we have provided an acidic medium. Whenever you provide an acidic medium to the alcohol, OH takes the H plus. OH takes the H plus and becomes a very good leaving group, H2O positive. So here the leaving group becomes OH2 positive. And this quickly leaves from here by SN1 mechanism, giving you a carbocation which is looking like this. Okay, and we know whenever the carbocations are formed, if they can shift to a better position adjacent to the adjacent carbon within one step, they will do that by hydride shift. So here, this is the carbocation. It asks the neighbor, do you want my plus? Neighbor has a hydride. We'll say, okay, we'll do a hydride shift. 1,2 hydride shift. Carbocation becomes stable, which is a tertiary one. Now the Br minus will come and attach as a nucleophile. Since there is no chiral carbon here, if it was a chiral carbon finally, I would get a racemic mixture. In SN1, racemic mixture is formed. But in this case, there is no possibility of any racemic mixture. So we get our product to be this one, which is B. Okay, I hope it is clear to everyone. SN1 reaction, do it with the rearrangement. Don't just simply remove the OH and put a Br there. Okay, it's a reaction going by SN1 mechanism in the acidic medium. Next one. Again, a similar question was done before. Now, again, we are doing correct order for the rate of alpha beta dehydrohalogenation, meaning E2 elimination. E2 elimination, when we do with alcoholic KOH, how do you decide the reactivity? Just make the final alkene and see the stability. If the final alkene is more stable, more substituted, in that case, you will see a faster rate of reaction. So in this case, I get a very, very good alkene because this is alpha carbon, this is beta carbon. If I remove the hydrogen, I get a butadiene, which is super stable alkene because of resonance. In the next one, I get a but1ene because there is no rearrangement possible here. So in this second one, I get a but1ene, which is not a very good alkene because of its unsubstituted, less substituted nature. Only 2 alpha hydrogens are present here. So less hyperconjugation, 2 alpha hydrogen. And on the last one, we can get a ZZ product. So with the E2 elimination, we get the ZZ product, which is but2ene, which is very nice as compared to the second one. Why? Because there are 3 alpha hydrogens here and 3 alpha hydrogens here. So there are total 6 alpha hydrogens, 6 hyperconjugations are there. But don't think here, sir, here to 0 alpha hydrogen, because resonance is more important or more stabilizing factor than hyperconjugation. So resonance has to be checked first. This is the best because of resonance. Resonance stabilized. So 1 is most reactive, then 3, and 2 is least reactive. 2 is least reactive. Okay, nice question. Moving to the next one. NEET 21 question. You can see here. Bond enthalpy order. Okay, very simple question, this one. When we know the size of the atom is small, bonds are stronger. So fluorine, chlorine, bromine, iodine, first option. Okay, alkyl fluorides are least reactive because of the highest bond enthalpy. Very difficult to break the bond. Moving to the next one. In a SN2 substitution, bimolecular substitution means a single step reaction, backside attack. RBr and Cl minus giving you RCl plus Br minus. Which of the following has highest reactivity rate? SN2 reactivity they are asking. We know SN2 reactivity is highest for primary alkyl halides, then secondary, worst are tertiary. Tertiary never react by SN2 only because they have a lot of steric hindrance on the alpha carbon and they are unreactive towards SN2 attack. So if I look at it, first one is primary, which is very, very good for us. Next one is next one is also primary, but on the primary, if I look at the beta carbon, a beta carbon is too bulky here. It has too many substituents. Not so good. Next one is primary, but then beta carbon is too much bulky. It carries a... So if I do a backside attack, you can see here, the alpha carbon, which carries a hydrogen, another hydrogen, and a tertiary butyl group. CH3, 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 something like this. NCERT has drawn a structure like this. Now, if a nucleophile comes to attack from the backside, you can feel yourself that how much difficulty it will face. So it's not a good reaction. Means it can undergo SN2, but not a great SN2 because of too much bulkiness. On this side only ethyl is there. On this side only methyl is there. So D is the best. D is the best. Here when the nucleophile comes to attack from the backside, at least a little bulkier alkyl ethyl is present. So it is still little bulkier. Okay, it is still little bulkier. When we have a methyl group, which is least bulkier, this will give you the best SN2 reaction. So best SN2 reactions are always going to be given by methyl bromide, then ethyl, methyl, then ethyl, because ethyl has some alkyl group, which is this one, then propyl, then your butyls may this one isobutyls are there, and then tertiary butyls and neopentyls, they will be having very, very poor reactivity. Okay. Moving on to the next one. Increasing order of nucleophilicity. When nothing is mentioned about the solvent, always take in water in a polar protic solvent. In a polar protic solvent, we should remember left to right what happens to nucleophilicity, top to bottom what happens to nucleophilicity. When you move left to right, nucleophilicity depends on electronegativity. Left to right, as we know, electronegativity increases. So, an electronegative atom would want to keep its electrons to itself, will be a poor nucleophile. So, electronegativity increases, so nucleophilicity decreases. Okay, so CH3 minus is a better nucleophile than NH2 minus, is a better nucleophile than OH minus, than a F minus. Okay, left to right decreases. Top to bottom, nucleophilicity depends on solvation effect. Solvation effect. As we know, when we go top to bottom, size of the ion increases. Larger the size of the ion, lesser would be its hydration or solvation. F minus is highly hydrated. F minus is highly hydrated, because of which it is very bulky and it's not a good nucleophile. Going down the group, when we go to I minus, it has very less amount of hydration. So it's overall a more, free moving iodide. So when in the polar protic solvents, when we take nucleophiles, when more hydration is there, nucleophilicity is poor, because F minus, when it moves, it feels a lot of resistance in movement because a lot of water molecules are sticking to it by ion dipole force of attraction, something like this. So many water molecules are sticking to it. So top to bottom, nucleophilicity increases. So nucleophilicity increases as solvation decreases. Solvation decreases. So I minus is the best nucleophile which we see in the Finkelstein reaction. So I minus, then Br minus, then Cl minus. Okay, I hope it makes sense. In the polar protic solvent, this is the order. In a polar aprotic solvent, there will not be any solvation. So we don't have to see solvation effect, we have to see the normal size. Then F minus is actually small as compared to I minus. F minus will be more mobile and easier to attack from the backside. So in that case, F minus will be a good nucleophile. So in a DMF solvent, DMSO solvent or acetone solvent, in that case fluoride is better, but in water iodide is better. I have told you the reason, solvation. Next one is hydrolysis reaction that takes place at slowest rate. Hydrolysis at the slowest rate among the following is. So these are the reactions which are happening. You can either check SN1, SN2, your wish. Slowest rate. If I see carefully, this one is an example of aryl halide. Aryl halide. Because we know aryl halides have some amount of mesomeric effect, the chlorine is sending electron like this to the benzene ring, because of which there is a partial double bond character between carbon and chlorine. Due to this partial double bond character, it's very, very difficult to, displace the chlorine. So they are very, very unreactive towards the nucleophilic substitution. They do undergo SN-AR mechanism, Dawes process, this is Dawes process reaction, which requires very, very high temperature of around 623 Kelvin and 300 atm pressure. So they are least reactive towards nucleophilic substitution, either by SN1 or SN2. First one can very easily give SN1, very reactive it will be because it's a very good carbocation. Third one can give very nice SN2 reaction, no problem. They will be highly reactive towards SN2. We don't have to make a carbocation. And last one will be very reactive towards SN1 because of good carbocation. So reactivity is very good in the case of 1, 3, 4, but very poor in the case of second option because of double bond character. Again, same question. Which of the following undergoes nucleophilic substitution, which is SN-AR mechanism, Dawes process mechanism? Why? Because we are talking about aryl halide chapter. Aryl halide. Whenever we talk about SN-AR mechanism, you need your carbon attached to chlorine to be more electropositive or electron deficient. If it is more electron deficient, in that case only your nucleophile can easily come and attack here. So a minus M group, a electron withdrawing group, when attached to ortho position or para position, will make it very much reactive. There is one reason, which is it increases the electron deficiency of alpha carbon. Another reason is it stabilizes the intermediate, which is called as Mesenheimer complex, which is a carbon ion. Okay, it's there in the NCRT or in your notes, you can check. So Mesenheimer complex will be stable if a minus M group is present. This is a plus hyperconjugation group, making it very less reactive. It will not be much positive. Very little positive it is. NO2 at the para position will be very nice. It will be highly positive. Reactivity will be very good. Dawes process, as you have seen, when I put one nitro group, uh, conditions eases a little bit. When I put two nitro group, conditions become very easy. When we put 3,3 nitro group to prepare picric acid, only warm water can do the hydrolysis. So yes, this is highly reactive. Most easily, A is highly reactive. OCH3 is a plus M group. Plus M group will send too many electrons, making it very less positive. So this is the least reactive. Least reactive. And this is somewhere in the middle. No group is there. So NO2 is helping here, which will make the Mesenheimer complex. This is how the Mesenheimer complex will form when the OH minus from the NaOH attacks here. This is called as a addition followed by elimination reaction. So first OH minus adds here like this. This pi become negative charge, giving you a carbon ion which looks like this as an intermediate. Cl, OH, pi, NO2. If you want to stabilize this, this is Mesenheimer complex. Looks like a rhenium cation, which is formed in the electrophilic substitution reactions. But this is not a rhenium ion, because a rhenium ion is a carbocation. This is a carbon ion. It is stabilized by NO2 by resonance. Minus become pi become pi become minus. So NO2 is pulling this minus charge, making it highly stable, and reaction will be the best in the A option. Next is most reactive towards SN1 reaction. Again, a carbocation type question. I want you to answer it yourself. Take it as a homework question number 1. Okay, tell me in the comment box who is most reactive for SN1. Draw the carbocation yourself and tell me which carbocation do you think reacts the, is the most stable one. I hope you are ready with your pens and notebooks and you are able to solve it. Next is tertiary alkyl halides are practically inert to substitution by SN2. Absolutely correct. Because of steric hindrance. I've already told you, because of steric hindrance, backside attack is very poor. Backside attack is not possible. So in that case, what will happen is only SN1 reactions will happen where tertiary carbocation will be stable. Next one, which is which of the following is the correct order of decreasing SN2 reactivity? Again, more steric hindrance, poor SN2 reactivity. Primary, secondary, tertiary. Primary is highly reactive, then tertiary not correct. Primary, secondary, tertiary. This is the correct order. Okay, primary alkyl halide, then secondary alkyl halide. Tertiary are the worst. Moving on to the next one. Next question is saying, consider the following bromides for SN1 reactivity. Carbocation formation. Removing here, making a carbocation. Primary not so good. Making a carbocation. Allylic carbocation has resonance. Very nice carbocation. Okay. Secondary carbocation, not as good as allyl because there is no resonance, but still good. So it has 2 plus 3, 5 hyperconjugation. 5 alpha hydrogens are there. Here, so we don't have to check, there is a resonance here. And here we have only 2 alpha hydrogens. So this will be the least reactive towards SN1. So 1 is least reactive, 2 is most reactive. First option. Okay, 2 is most reactive, then 3, then 1. Okay, so you can see how similar questions keep repeating almost year after year from SN1, SN2. Very simple question. They will not be much difficult in the NEET. Basics should be clear. See again 2014 question, SN2 reaction, correct order of reactivity. Just now we have solved it. I hope you will be able to do yourself. I told you about these two. In these two, this is more reactive. So this is a wrong order because SN2 means steric hindrance. Least steric hindrance will be there in the CH3Cl, which is this, then this. So D option. Okay, methyl chloride, then ethyl chloride, and then your secondary, tertiary would be the worst. Primary, primary with the least bulkier alkyl. Next is increasing order of reactivity towards SN1. Again, you see J 2017 question. Same questions keep repeating almost every year. So very important SN1, SN2 reactivity. Some chlorides are given. I'm drawing them. So SN1 meaning carbocation. Cl minus goes out, carbocation forms. Cl minus goes out, carbocation form. This one is secondary. This one is primary. So anyways, this is better than this. One is better than second one. Okay, up to here we have reached to. We can eliminate a few options maybe. One is better than 2, one is better than 2, one is better than 2. So this is wrong. One is better than 2, one is better than 2. Okay, so one option we have eliminated. Next one is a benzyl carbocation, which is very good. CH2 plus, then this is phenyl ring. Phenyl CH2 plus, resonance is there. Nothing can beat it. And on the top of it, there is a OCH3 group, which is acting like a plus M and sending a lot of electrons there. This is super good. Super good. OCH3, the methoxy group, makes it even more stable. So we get the answer 3 is the best, then 1, and 2 is the worst here. Okay. 3, 1, 2. See, 2019 SN1. Repeatedly questions are getting asked. I hope you will be able to do same question. Just now we did. Okay. This is a very good carbocation because of OCH3, which will provide plus M effect. This is also a very good carbocation, although no plus M, but still resonance is there. It is good. This is super good. This carbocation versus this carbocation. Now, among these two comes a small, case that we should remember. We can easily do the elimination by telling that 3 is the best, then 4th. So although these two options you're getting here, 3 is the best, then the 4th one. Okay. Among the carbocation, which is ethyl carbocation and isobutyl carbocation, which carbocation is better is a little bit of a factual point that we need to think of. Okay. That we need to think of. Actually, whenever small alkyl, primary alkyl carbocations are there, no, they are never stable. Although hyperconjugations are more present here. There are 3 alpha hydrogens here and there is only 1 alpha hydrogen. Okay, but in the small alkyls, the carbocations are never found to be stable. So ethyl carbocation, propyl, actually better than ethyl is propyl. It is completely a factual point. You should remember, better than ethyl is a propyl carbocation. Better than propyl is a butyl carbocation. Okay, so don't consider the hyperconjugation effect in simple alkyls. So when primary simple alkyls are there, they are not good carbocations. As the alkyl group become bulkier and bulkier, more plus I effect will decide the stability of carbocation. So more the plus I, more the stability. Here this will have much more plus I. So this will be somewhat better than the ethyl one. So this is little bit of a factual point you can remember. This is okay. This is the worst. Okay, hyperconjugation generally decides whenever we take bulkier or we can say a secondary or a tertiary alkyl halides. But when we take primary, in primary it's mostly the inductive effect who decides the stability of carbocations. Little exceptional thing that you should remember for this one. Okay, in the NCERT also towards the reactivity of SN1, they have given a few compounds where isobutyl is given, which is this one. Okay, isobutyl is given and N-butyl is given. They have written isobutyl is more reactive. That means we are not checking for the alpha hydrogens. Instead, we are checking for inductive effect. So remember it, N-butyl, then isobutyl, like this. So this is something you should remember about it. So here the option should be accordingly 1 better than 2. 1 better than 2, which is option A. Okay, 1 better than 2. Little bit of a tricky one. Moving ahead, reactivity towards nucleophilic substitution by SN2 mechanism. Again, see repeated question SN2. So don't make a carbocation. When you want good reactivity towards SN2, you want your carbon carrying the halogen to be very much, electron deficient. So I need it to be electron deficient. Here this NO2 is helping. Here this NO2 is helping. Here none of the NO2 is helping, because this NO2 is pulling the electrons by minus M effect. This NO2 is also pulling the electron by minus M effect. And here only pulling by minus I effect, which is almost negligible at the third position anyways. Okay. So first thing we should do is we should try to eliminate the option. These NO2s are all helping for the SN2 reaction. So this one has to be the worst. Here nobody is there to help. So these are all positive carbons. But this one is very, very little positive. This is 1 point. Okay. So 1 has to be the worst. 3 options are there where 1 is the worst. Then we'll go to 4th one. I just told you why. Why? Because in the 4th one, NO2s are only applying a minus I effect, which is a very weak effect. Now coming to these two. So we have got to 1 and 4th. Among these two now, on this case, minus M effect is same. Right? And here, minus I effect is also same for the meta one. So meta one is same. I can neglect the meta position. Whatever meta NO2 is there, it is doing the same thing in both the sides. But this NO2 at ortho position will apply some minus I as well, maximum minus I. Here minus I would be minimum, making it most positive and most reactive. So this is another tricky question where little bit more of depth you had to see. So I just want to check the positive nature of the carbon, alpha carbon. This one seems to be most positive. So 2 will be more reactive than 3. 2, 3, 4, 1. Okay, so little trickier questions we have dealt with. Next one is, for the above reaction, which of the following reaction condition is true? This is your Dow's process. We have to remember it is 623 Kelvin, 300 atm pressure with the NaOH. 623 Kelvin, 300 atm pressure, Dow's process. I hope it is clear to everyone. Next one, what is product P? 2021 question. Mg with the alkyl halide gives you what? It gives you Grignard reagent, which will look like this. MgCl, partial minus, partial plus. Then you are putting ethanol. Ethanol with Grignard reagent. Ethanol is just the acidic compound which will just provide you a H positive. Any other way to Grignard anyways cannot do anything to the ethanol. There is no unsaturation. So just this Grignard will go and collect this proton, giving you cyclopentane. So B would be the answer. Right? B would be the answer. Same thing would happen if we take, water also, if we take benzoic acid also, if we take phenol also. All acidic compounds just are going to provide a proton to the Grignard, giving you alkane formation. Nucleophilicity, I just have told you in the last 2-3 slides back. Fluoride OH minus, fluoride is not good. OH minus is better, because left to right nucleophilicity decreases. Water and OH minus, whenever a negative nucleophile is there, negative is always better than neutral. Negative nucleophiles are better than neutral nucleophiles because they have a proper minus charge. This is also again negative neutral. So this is correct. NH2 minus is a negative nucleophile which will be more, electron rich than a neutral nucleophile. 28th one, 2023 NEET question. Question is, there is a carboxylic acid and we are putting a X into it followed by hydrolysis and we are getting a alcohol. Means some reduction we are doing. Some reduction we are doing here. And in the next one, we are putting X. Same thing we are putting here as well. And we are getting a anti-Markovnikov alcohol. Anti-Markovnikov alcohol. So it has to be hydroboration oxidation reaction. So where X is going to be BH3 or B2H6. And yes, we know BH3 also reduces our carboxylic acid into primary alcohols. BH3 can do that and LiAlH4 can do that. Right? So it's a good question. We can get B2H6 here. B2H6. H2PD cannot reduce your carboxylic acid. It will not even do this. It will make a alkane here. NaBH4 anyways will not react anywhere with the both of them. LiLH4 will give the first compound, but not the second one, right? Next one says, in Lucas test, it's a NEET 22 question, primary, secondary, tertiary alcohols are distinguished on the basis of their reactivity with HCl, ZnCl2 known as Lucas reagent. Absolutely correct. Where tertiary alcohols give you immediate turbidity because they produce tertiary alkyl halides within no time, within a few seconds. Secondary give you turbidity after 5 minutes and primary require heating for the reaction. Primary are most reactive, not at all. It's a wrong question. It's a SN1 mechanism for tertiary. So tertiary are most reactive, then secondary, and primary are least reactive. So statement 1 is correct, but 2 is incorrect. 2 is incorrect. So fourth option. I hope it is you are feeling more confident after looking at the easy questions because NEET ask easy organic chemistry. They don't ask too much of difficult. Just follow the NCERT. If you are following the NCERT, all the reagents of NCERT you are clear with, there is no problem that you are going to get from the organic chemistry. Next is acetone reacting with Grignard reagent. Very famous reaction to prepare tertiary alcohol. Whenever ketones react with Grignard, C2H5 minus, attack happens like this. First reaction we did today was also same type. So we get, after hydrolysis, we get OH and a ethyl group has attached here. So what is the name of this product? Do the IUPAC nomenclature now. This carbon is the most important carbon for us. So it should be there in the parent chain. Take the longest chain, 1, 2, 3, 4. This is the longest chain where we will start numbering from here, 1, 2, 3, 4. It's a 2-methyl, 2-butanol. 2-methyl, 2-butanol. Okay, 2-methyl butane 2-ol. This is our final product, right? Moving on to the next one. Next question is again from NEET 2021. NaBH4 which never reacts with acid nor with acid derivatives, but it can react with aldehyde ketones. It can react with aldehyde ketones. So it can reduce your ketone to alcohol, but will not touch the carboxylic acid group. And they will not touch the carboxylic acid derivative group. Ester will not be reduced. They did not give any, hydrolysis. So if hydrolysis was given, I would have converted this into carboxylic acid, but they didn't give that. So let's only reduce ketone. This is wrong. This is right, but this is wrong. This is right. This is absolutely right. So we get our C option. This is right, but this is wrong. Okay. So this is the one as the final answer, C. Moving on to the next one. Next question that we are taking here is when vapors of secondary alcohols are passed over red hot copper 573 Kelvin. Copper is a dehydrogenating agent. Dehydrogenation it will do for primary and secondary alcohols. So whenever we take a primary alcohol, all of you should know it gives you a, this is a primary alcohol. Dehydrogenation happens like this. On the red hot copper, we get a aldehyde. On a secondary alcohol, we get a ketone. dehydrogenation using copper 573, we get a ketone. And tertiary do not undergo dehydrogenation because anyways there is no beta hydrogen present. It undergoes dehydration. Tertiary gives alkene. Just like a E2 elimination reaction, we get a ZZF alkene, but secondary would give you a ketone, which is option D. Okay, a simple question, option D. It's a NEET 2019 question, which is not the product of dehydration of this compound. Now it's a good question because we need to know the mechanism. It's a E1 mechanism. In the previous class, when I explained to you preparation of alkenes from alcohols, we have discussed this particular problem. Okay, we have discussed this particular problem, this type of problem, that it's a E1 mechanism. So this is the compound that we are starting with. E1 mechanism. OH takes the H plus and water gets removed, giving you a nice carbocation, which is a tertiary carbocation, giving you a nice carbocation. Now think, from this carbocation, this is beta, this is beta, this is beta. One product can be formed here, which is this one. This though is possible. One product can be formed here. This is also possible. And one product can form from this beta also. This is also possible. Not all of them are not equally possible. Means some of them will be major, one of them will be minor. Said Zeph Hoffman. But what about this one? See, for this product to form, first the carbocation need to shift to this side. Why would a tertiary carbocation shift to become another tertiary carbocation? It's not correct. We should not do that. It's already a stable carbocation. So we should not do any rearrangement. No rearrangement. So yes, B is not a possible alkene for this reaction. It's a nice question. Don't do the rearrangement, because if we do the rearrangement, we reach to another tertiary carbocation, which is not more stable than the previous one. We can only do the rearrangement when the new carbocation formed must be, more stable than the previous one. Next one, dehydration of alcohol is E1 elimination, and always tertiary carbocations are better than secondary and primary. So tertiary, then secondary, then primary. This will not undergo any dehydration only. So A option. Okay, this doesn't have any beta proton. It can still undergo intermolecular dehydration to give alcohols, but it will not react with the H2SO4 to give any alkene. So tertiary is the best carbocation stability, E1 mechanism. Most suitable reagent for the conversion of alcohols to aldehyde. We require a very, very mild oxidizing agent here, which is PDC. You can take pyridinium dichromate, PCC, pyridinium chlorochromate. You can take CrO3 in the anhydrous medium, like CrO3 plus, chromyl chloride, they can tell. CrO3 plus acetone, they can tell. CrO3 in ether, they can tell. Anhydrous condition. These are mild oxidizing. Or copper 573 also I can use, which is your, okay. So PCC is the most suitable one here. CrO3, they didn't mention which CrO3. If it is in the acidic medium, it would be Jones reagent, which will become a strong agent. So best option looks C here, which is PCC or PDC, both you can use. Okay. Moving on to the next one. An unknown alcohol is treated with the Lucas reagent to determine whether the alcohol is primary, secondary or tertiary. Which alcohol reacts fastest tertiary by what mechanism? SN1. Just now we have discussed. Tertiary alcohol by SN1 mechanism. Immediate turbidity we get. Most suitable reagent for the conversion of primary alcohol to aldehyde. Just now we had done it. I think it's a repeated one. The same question got repeated maybe 2 times. It's, by chance we have only put it twice. This compound cannot be prepared by which reaction? Now, I can first do is verify the number of carbons. 1, 2, 3, 4 and 6. 10 carbons I need. In the first one, I have 1, 2, 3, 4, 10. Okay. 1, 2, you know, 8, 9, 10. Okay. 6, 7, 8, 9, 10 maybe. This is just a printing mistake, I guess. And this is 1, 6, 1 plus 6, 7, 8, 9, 10. All of them are giving us 10 carbon. So we have to just think carefully and draw the product now for each one of the case. In this case, I am taking a skeleton of, butane 2-one, which is looking like this. Here double bond O is present. There the phenyl is coming to attack. So phenyl, after it attacks, this alcohol I can get, which is a ethyl methyl phenyl OH. Ethyl methyl phenyl. This is giving us the product. Next one, there is a phenyl acetophenone we have taken. There is a CH3. When the ethyl group comes and attack here, you get this, which is again the same thing, only ethyl group, methyl group, phenyl group, and a OH. So yes, this is also giving you the product. I'm checking the last one now. Last one would give you a primary alcohol. So I think this is just written by mistake, this one. Last one will give you a primary alcohol because, as you can all see, it's a formaldehyde. Formaldehyde, when the Grignard will attack, whatever the Grignard is looking like, it will give you a primary alcohol. But we need a tertiary alcohol, so we need to attack it on ketone. So D will not give you the correct product. Okay, D will not give you the correct product. What is the major product of the following reaction? This is the reaction given, as you can see. Again, it's a question which NEET also asked in 2024. I told you. When you attack Grignard on CN, only one time attack will happen. But when you attack it on a ester, this is the ester, C double bond O, OCH3. I'm writing it again. This is the compound they've taken. On the ester, attack occurs two times. Grignard will attack first time, OR will go out, ketone will form. Then it will attack second time, then it will become a final alcohol. So one attack occurs here, two times attack occurs here. So top one will become a imine. Top one will become a imine. C, CH3, double bond, N, MgBr. And the bottom carbon was first ester. First attack happened. CH3 came and attacked. It became a ketone. Then next time on a ketone, again an attack happened. It became a tertiary alcoholic group. Now if you do hydrolysis, this will convert to ketone, as I told. So top will be acetophenone and the bottom will be CH3CH3OH, which is option B. Nice question. Similar question in NEET 25 we have seen. Same question, similar question in J24. This is wrong because cyanides are getting attacked. This is wrong because they have not attacked on ester. This is wrong, they didn't attack on the cyanide. Okay, next one, zinc amalgam HCl, which is Clemmensen reduction. Clemmensen's reduction, which occurs only on aldehydes and ketones. It converts aldehyde and ketones. It gives them 4 nascent hydrogen and convert them to alkanes. So I can see the functional group carefully first. This is a ester. Nothing will happen here. This is a ketone. This will break and 2 nascent hydrogens to this oxygen, 2 nascent hydrogens to this carbon. This is a aldehyde. Here also 2 nascent hydrogen to the oxygen, 2 nascent hydrogen to the carbon. So it will become a methyl group. This is wrong. This is wrong. This is the one. This is wrong. Okay, this would have happened with LiAlH4. With LiAlH4, both would have converted to alcohol. Ester also would have converted to alcohol. With LiAlH4 or hydrogen palladium, you would have reached here. If you want to go here, H2PD you could have done. If you wanted to go here, you could have done NaBH4, because we know NaBH4 does not attack on acid derivatives. It will still reduce your aldehyde. But there is a ketone here, so ketone will not give a primary alcohol. A secondary alcohol, if it was given, that would be correct. If this was a secondary alcohol given, they gave a primary alcohol, so anyways these are incorrect options, so C is correct. With phenyl magnesium bromide, they're asking reaction, which is nucleophilic addition reaction. This is from the aldehyde ketones chapter when you study this reaction as a mechanism. Aldehydes are more reactive due to two reasons. One is electronic reason, one is steric reason. Aldehydes have less steric hindrance for the attack of nucleophile. So I can see here this is a aldehyde. This would be most reactive because there is only one bulky group, one side small group. Here two bulky group. Here two very bulky groups. This will be least reactive. This will be most reactive. This will be middle. 2, 3, 1. Option B. Okay. So these are the type of questions that we have discussed in today's class. One or two more questions we will just see for the day. With phenol, so a few reactions of phenol we can directly revise it from here, and phenol chapter gets revised like from here directly. NaOH plus CO2 in the presence of H plus. So first NaOH will make it phenoxide, then this is Kolb's carboxylation reaction, which will give you finally salicylate. On acidification, salicylic acid. One matches with 4. One matches with 4. With aqueous NaOH, chloroform, this is our nothing but Riemann-Tiemann reaction, we get salicylaldehyde. Option B matches with 3. Zinc dust, which is reduction to benzene, preparation of benzene. And with the dichromate or dichromic acid, it gives you benzoquinone, which is a dark colored compound. Aniline also gives this. This is benzoquinone. Aniline also gives this. Phenol also gives the same. D1. So option D. Okay. So this is our today's class, and we have revised alkyl halides, alcohols, phenols topic in the today's class. I hope all of you have enjoyed the class and you would like this video after doing this, and you will study very hard for your dream of becoming a doctor very soon in the next 30 days or so. So all the very best. See you all in the next class with thermodynamics topic tomorrow. Bye bye. Thank you.